This video is designed to talk about sinusoidal traveling waves, meaning a wave pulse that looks like a sine wave. Give me just a second. I think the best thing to do is actually start with a screen share and then come back to this. Okay, so I've got this video, this simulation paused right now, but you can see what looks like a sine wave on the screen. And maybe I'll mention a few things here. This is the x-axis. Up here is the y-axis. Both of those have units of meters. Okay. And now I want you to watch carefully this sphere at the origin, right? I want you to watch how it moves. Does it move up, down, left, right, etc. when I hit the animation? And it's going to look a little bit trippy if you stare at it too long, but I want you to try and see which way you think this wave is traveling, to the left or to the right. Okay, so let me get rid of that last one and let's run this thing. Here we go. So notice the red ball at the origin is going up and down, but the wave is actually traveling to the right. So in this case, we see a wave traveling to the right. What does that tell us? I'm going to mention something here. We know that y takes on the form y of x plus or minus vt. So in this case, we're expecting it, because it's traveling to the right, should you use the plus or the minus? We're going to use the minus. So it's a function of x minus vt. And in the last video, I alluded to this. You could also write this as y is of the form, it's a function of kx minus omega t, meaning every time you see a kx, you'd better see a minus omega t with it. All right, so let's go ahead and stop that share, and let's pause this and go to the whiteboard. All right, so, and let me turn this on for a second so we get less glare. All right, so what I was saying there is the shape of the wave, of this sinusoidal traveling wave, and I should be clear, it's a transverse. We'll talk about sound waves in the next chapter, and that's the example of longitudinal, so we'll go more into longitudinal waves then. But the shape of this wave is y as a function of x and t. You tell me where you're at and what time it is, and I'll tell you how far up or down that piece of the string or that piece of the medium is. Okay, so we're going to go, what do these symbols all mean? And to be clear here, this was the snapshot before we started at time was equal to 0. A is called the amplitude. Just like an oscillation, we have an amplitude. And I'm going to try and draw it like this. The distance, how about I go from here, there. This distance here is one amplitude, and this distance here is also an amplitude, so this would be negative A, right? How about I just say it like that? Or if I go, the distance between here and here is twice the amplitude. So the distance between a crest and a trough is twice the amplitude. Or from the equilibrium position to the top to the crest is one amplitude. So that's the amplitude. Let's go ahead and leave it at that. Or I could, in units of meters. Obviously, you could have feet or whatever, but we're right. That's going to be a distance. Remember the units on here. Y is a shape. It's a distance. X, the length. That's going to be in meters. All right. Lambda is called the wavelength. Also in meters. And the wavelength is going to be it has to be a length Wait, that's not the wavelength. That's half a wavelength. Whoops, my bad. Let's go, how about, let's use the bottom. We'll go from the trough to trough. That's better. So this distance here is wavelength. Lambda, Greek letter lambda. Kind of looks like an upside down Y. All right. And so you could measure it from trough to trough. You could measure it from crest to crest. I just ran out of room. You could also measure it from equilibrium point. And this is where I kind of screwed up in my head. You have to go to not to the next equilibrium point, but two over, right? It has to be where you get to the same spot in the wave again. So the wavelength is usually measured from crest to crest or trough to trough because you're less likely to screw up like I did. K is a thing called wave number. The equation for it is 2 pi over the wavelength. It turns out it's very convenient to use K because we get something that has no units, which has the correct units, not degrees, radians, right? So K times X must have no units. The units are meters to the -1. Okay, so in this case, right, 2 pi over meters should have units of meters to the -1, or 1 over meters if you want to say it that way. But notice this makes sense. The argument of a trig function must have no units. 1 over meters times meters gives you no units. So notice we're going to have to be using radians. All right, that's good to know. T, I can't show you the period on this plot. Nothing on this plot has to do with time except for the fact that, yeah, I took one picture in time. The squeaky marker, huh? Sorry about that. Good enough. Can you read that? It's the time for one element to undergo one full oscillation. Like that one element, meaning like the one ball that was at the origin, it went up, and then it went down, and then it came back. So that would be one full oscillation, the time to start. It was starting at the origin going upwards. How long until it returns to the origin going upwards? So it went up, down, back. That's one period. Frequency. 1 over the period. So a lot of this probably seems familiar from the chapter on oscillations. The main difference is K is wave number now. Okay, so this is frequency. I tried to get a different blue marker. All of them are giving me trouble today, so I apologize. This one's so squeaky. Okay, F is frequency in hertz, or 1 over seconds, or seconds to the -1. To be clear, period is a time. Time is measured in seconds. I didn't have room to write the units in. Sorry about that. I'll write it like that, so it's all right. Seconds. Omega is angular frequency. Radians per second. It's 2 pi f, or sometimes we'll write 2 pi over the period. Does that fit on the screen? Yeah, it's getting pretty weak there. Let me try this other blue, even though it's bad. It's bad too. For some reason, all the blue markers are bad here. All right. Just to be sure you can read that. Let's not kid around. All right, that shows up a little bit better. So these symbols probably seem familiar from oscillations. Wave speed is a little bit different. I mentioned this in the last video. but I don't think I mentioned it this way. V is equal to F lambda. Now let's think about the units. 1/seconds times meters is meters per second. That looks good. That's one way to do it. Now it turns out if you do a little bit of chicanery here, if we plug in, if we use if we use this equation to solve for omega, to solve for F, and if we use this equation to solve for K, you could rewrite the wave speed in terms of omega and K. So if you want to pause the video and do that on your own, go ahead and pause now. I'm going to proceed. So if we use this and flip this all around, hopefully through algebra, you could show that V is equal to omega over K, right? And that's the wave speed, right? You may hear later about things like phase velocity and group velocity. More on that some other time, okay? Here, we're talking about the speed at which energy travels down the string, all right? One last little thing that's mentioned in here, phi. What is phi? That's a phase angle. If we set x equal to 0 and t equal to 0, that's basically saying what is the position of the ball at the origin at time equals 0. And you can use the phase angle to adjust that position. So we're using a sine wave for our waves, and we're using a cosine function for our oscillations chapter. So that's how I'm going to try and keep them straight on the equation sheet. But the point being is you can switch a sine wave to a cosine wave by adjusting the phase angle. So you can pick any starting point you want, and that's what this is on. We'll do more examples on phase angles later. All right. One thing that is a little bit tricky here, you might notice that I could use a phase angle of 0, or I could use a phase angle of 180. But those shouldn't give the same results. Only one of these makes sense. So it turns out the phase angle, we usually use the initial position and the initial velocity. It's at the origin moving upwards would give us a phase angle of 0 here. If it's at the origin and moving downwards, that would correspond to a phase angle. That would look like if it shifted 180 degrees. So that would be a phase angle of 180. More on that later. And again, I should mention here, this minus sign here means moving to the right. Okay, if I had used a plus sign here, I'd be moving left. How do I know it's right, left as opposed to up, down? Because it says X here. X with the minus sign moving right. X with the plus sign moving left. If I had, say, Z with the plus sign, that would be moving into the page. Z with a minus sign would be moving out of the page. So that's how you can. Now, this, you heard me mention velocity. Let's go look at this whiteboard too and talk about the velocity in a different way. Okay, the shape of the wave was given by this long equation. Now, I want you to notice carefully here. Let me just draw this again. V subscript y. This is vertical velocity of element at x. Let me say position x. And I suppose I should write that in black. I apologize. Okay, so what am I talking about here? I'm talking about the up and down velocity of the ball that was at the origin, right? There was a ball at the origin moving up and down. So it's the velocity in the y direction, but it depends on what time you look at it and also which position on the rope you look at it. Is it there? Is it at the origin? Is it at the right end? Okay, so if you tell me the x coordinate on the rope and you tell me what time it is, I should be able to tell you how fast that ball is moving up and down. Well, you just take a derivative of this thing with respect to, think, time. Okay, we want dy dt. Now, we're going to assume the x position, right, where you're at on the rope is not changing in time. So we're going to pick one. So you could argue here, maybe I should use a partial derivative, right? Because I'm going to pick one spot on the rope and set x to some constant. When you do that, let's take a look. Well, if you want to pause the video, great. I'll give you the answer in a second here. Here I go. So in this case, you're going to take a derivative of this. We should get a cosine function. Derivative of sine is cosine, not negative. So I'll get a amplitude as a constant. And then we're going to get a cosine function. Then our phase angle. Right? But now think, we take the derivative of what's inside with respect to t. So it looks like I'm getting what? A minus omega popping out? Come on. Man, this marker. You know what? Sorry, the color coding stinks. All right. Let me make sure I'm where I want to be. Okay, good. If we take a second derivative of this, we can get the acceleration in the y direction. Again, that depends on the position and the time, right? The acceleration of something that's wiggling up and down, well, you could take another derivative of that. If you want to pause the video and write down what you think, this is the time. I'm going to write the answer in just a second. Okay, here we go. Make sure I got that right. Okay. Now you might be saying, whoa, hold up, dude. Derivative of cosine is minus sine. So shouldn't that minus sign cancel this one? Okay, I'll give you that. But then you're going to take another derivative of this one and get another minus sign. So you're actually going to have a minus sign from here, a minus sign from the derivative, and a minus sign from the chain rule derivative part. And so you'll actually get three minus signs. -1 times -1 times -1 is negative. Oh, shoot. This is wrong because it switches to a sine function. So we see the function keeps changing. All right. And so is there anything else I want to say about that? Maybe I'll mention a couple more things for string waves in particular. We're going to know that the velocity is equal to the square root of tension over mu. Mu is mass per length, or kilograms per meter, or linear mass density. Make sure that's still on the whiteboard. Focus issue, come on. What is this? Okay, there we go. And just so I don't screw this up, we've been talking about energy being transmitted. Well, the rate at which energy is transferred, we're talking about energy per unit time. That's joules per second. That has to do with power. I'm going to use this kind of puffy looking P for power. And I happen to have this on average. The power transmitted is 1/2 mu. What else do we get there? V. And I think that's kind of an interesting equation worth mentioning. We can see that the rate at which energy transfers depends on the amplitude squared. Right? And it depends on the frequency squared. I said frequency, this is really angular frequency. I hope you get the idea. Remember, omega equals 2 pi f, they're the same thing, basically. Right? The density, how heavy the string is, and the speed. So these are the factors that affect the rate of energy transmission, the power. All right, that's enough on this. We'll do some worked examples in the next